left off last time, we were just about to talk about Sato-Tate for non-CM elliptic curves and relate this to L functions. But I've decided that I want to move on to talk about Sato-Tate groups because this is going to be very important for the project groups who are going to be working over the next few nights. And if I have time, I'll come back in lecture 4 and give the connection between L functions and the Sato-Tate conjecture for elliptic curves over Q without CM. Okay. So Sato-Tate groups. So I'm going to start with the case we already pretty much understand, which is Sato-Tate groups of elliptic curves. Okay, so we're going to embed the unit U1 into SU2 via the map that just sends U to U0 jar U bar. And in the previous lectures, we found 3 subgroups. So that's U00 U bar. Okay? 3 subgroups, I'll try to write a little bigger, of SU2 whose Haar measures control the distribution of normalized Frobenius traces. Okay, so the 3 groups we found were U1 and the Haar measure, at least the push forward of the Haar measure onto conjugacy classes, which we can write in terms of the eigenangle we found was just 1 over pi d theta, uniform measure. So every element of SU2 is conjugate, it's diagonalizable, so it's conjugate to a matrix that looks like this. So the theta, this is the theta here. And so there's a 1-to-1 correspondence between thetas, so thetas and 0 to pi. And so d theta is the Lebesgue measure on 0 to pi. And so this case arises when we have an elliptic curve with CM over its field of definition. So we're talking about elliptic curves E over K. And then the next group we found was the normalizer, the unitary group under this embedding, so the normalizer in SU2. And here the measure, push forward to the Haar measure, looks like, well, we have the identity component, which looks like half of this measure. But then we also have the non-identity component, which is just half of the Dirac measure, which puts us 0 at the angle pi over 2. And this was the situation where we had CM but not defined over K. So that, for example, a CM, an elliptic curve over Q with CM, this is what we would see. And then the third case, the generic case, is we get all of SU2. And in this case, the measure looks like 2 over pi sine squared theta d theta. Okay. And so we're thinking of, in terms of our equidistribution statements, we're always talking about equidistribution in the set of conjugacy classes of our Sato-Tate group. Let G denote our Sato-Tate group, which in this SU2 case I've just identified by expressing it in terms of eigenangles with this interval 0 to pi. And so our measure, in terms of the terminology that we defined in the previous lecture as a linear functional on the Banach space of continuous c-valued functions on our set X, with the quotient topology we get from taking the topology on G and quotienting by the conjugacy relation. Well, this just sends a function f to its integral over 0 to pi. Okay, so that's just reviewing what we've done in the last 2 lectures. So I've been calling this the Sato-Tate group, but I really shouldn't be saying that, because these are just groups that we happened to find whose Haar measures happen to give the distribution of normalized Frobenius traces that we observed, and then we actually proved that they do. At least in all the cases, in this non-CM case, this is proved at least when K is a totally real field. But now I want to give a different, an explicit definition of the Sato-Tate group that's intrinsic to the elliptic curve itself and has nothing to do with equidistribution at all. It's simply an arithmetic invariant attached to the elliptic curve. And in general, we're going to make this more explicit as we go along, but let me just say in general what we're looking for. So we're going to be thinking about Sato-Tate groups in dimension, say, G. We'll start with G equals 1, but here we're thinking of an abelian variety of dimension G, or equivalently a curve of genus G. Or not equivalently, but they would coincide in the case where the abelian variety was the Jacobian of a curve. So there's going to be two pieces to our definition. One is we're going to have some compact Lie group, and not just any, I don't just mean that abstractly, we're going to explicitly embed it up to conjugacy as a linear group, say in GL2G, and the embedding is important. This won't come up today, but we'll see in the next lecture examples in dimension 3 where you can have two Sato-Tate groups that are isomorphic as abstract Lie groups, but their embedding in what will turn out to be USP6 is different, and they give rise to different trace distributions, or more generally different L polynomial distributions. Okay, so it's important to be explicit about this. But then the group in and of itself doesn't tell us that much. What we really care about is the fact that we've got a map from primes, good primes where our variety has good reduction, to conjugacy, the set of conjugacy classes. So for each prime P, we're going to get a conjugacy class, call it X sub P. And we don't want our group to be any bigger than it needs to be, so we'll generally, this will be ensured by our definition. We want this sequence of conjugacy classes to have dense image, and most importantly, we want to be able to relate it to the thing we actually care about, the distributional questions related to the trace and more generally to the normalized L polynomials. So we want the characteristic polynomial of our conjugacy class X sub P. This should be equal to the normalized L polynomial. Okay, for all but a finite set of primes P that we're happy to ignore. And then, so we could think of this as two pieces. There's a group and a sequence indexed by primes of the number field. And we're going to assume that the primes are ordered by norm. Break ties arbitrarily. It doesn't affect the equidistribution statement. And then, so this is just data associated that we can associate to an abelian variety. And then the Sato-Tate conjecture is simply the statement that this sequence X sub P is equidistributed in the very precise sense that we formalized last time. So we mean this is a sequence of conjugacy classes. We mean equidistributed with respect to the push forward of the Haar measure on the group. Okay. All right. So I just want to, so we sort of started this from the other direction. We started from the equidistribution, and then we found these groups that explain the distribution that we're seeing. But now I want to give an intrinsic definition that will allow us to, given an abelian variety, determine what define its Sato-Tate group and understand it, even if we can't prove an equidistribution result. At least we know what equidistribution result we should be trying to prove. Okay. All right. Okay. And maybe just one other remark before I get into the specifics in dimension 1. This recipe or this setup here, this is quite general. This can be applied not just to abelian varieties, but motives of arbitrary weight, or even more generally to L functions. I mean, if I have a sequence, an L function that is, say, an arithmetic L function in the sense that it has an Euler product and satisfies a functional equation, and I know that I can think of that as giving me a sequence of polynomials. Probably I want it to have rational coefficients, and I could ask equidistribution questions about that sequence of L polynomials, and then I might look for a way to associate a group that would give me whose Haar measure would give me the distribution of those L polynomials. Okay, so this is a very general setup. All right, now let's get down to brass tacks. So recall, I think Alina defined this for us, the L-adic Tate module. So this is just the inverse limit, of course, of the L to the n torsion subgroups. And we know that this is a free ZL module of rank 2. And then we have an associated Galois representation, L-adic Galois representation, say from our absolute Galois group into the automorphisms of the Tate module. which after we choose a basis, we can think of as GL2 Z mod L. Okay. And I'll note that the key thing we care about with this Galois representation is that if we take the characteristic polynomial of the image of one of our absolute Frobenius elements at a prime where we have good reduction, this is going to be the same thing as the characteristic polynomial of our, well, with the coefficients reversed, but we can relate it to the characteristic polynomial of the Frobenius endomorphism of the reduction of our elliptic curve at that prime. Okay, so maybe I'll put an approximate there. Okay, for all good primes. And then now our goal is to eventually get a matrix group with complex coefficients. So the first thing we'd like to do is, let's not work over a ring, let's work over a field. So we'll define the rational Tate module, we'll just tensor our Tate module with QL, or with Q, I guess, give us QL coefficients. And so now we're going to think of our L-adic Galois representation as landing in GL2 QL. Okay. So now we're interested in the image of this Galois representation. So let's write G sub L for the image of our L-adic representation, which is now going to be a subgroup of GL2 QL. Okay. Now we want to convert this into an algebraic group. So we're going to define GL, put a little czar in the superscript. This will be the Zariski closure of GL, which is just a set in this algebraic group. So we're thinking of GL2 over QL. Okay, and so for those who might not be familiar with algebraic groups, this is a standard construction. We can define, so an algebraic group is for me, when I say algebraic group, I mean an affine or linear algebraic group. So this is simultaneously an affine variety whose group operations can be defined by morphisms. GL2 I can define over any field. Here I'm thinking of it as being defined over QL. G sub L is a subset of the QL points on this algebraic group. I can now take the Zariski closure of that as a set, and then, wonder of wonders, it turns out one of the first things you prove when you're working in algebraic groups is that it turns out to actually also be a group, and so we get an algebraic group over QL. So this is going to be a QL algebraic group. Okay. So that means it can be defined by as the zero locus of a set of polynomials with QL coefficients. Now we're going to define another algebraic group, which I'll denote GL1 Zariski, by just taking the intersection with SP. So I guess we want SP2. So this is as algebraic groups, and explicitly, you could think of this, we're going to impose this symplectic condition. Oops, sorry, that's an M. We want it to preserve a symplectic form. Just to be explicit, let's pick one, say this form. Okay, so we want M transpose times our form times M to give us back the form. Now, turns out I could have just told you we wanted to. So this, well, first off, we should be clear that this is a condition we could define as a polynomial constraint. So this makes sense as an algebraic group. Now, since we're in dimension 2 or dimension 1, but we're in SP2, it turns out that SP2 is actually equal to SL2. So I could have just instead said, let's restrict to determinant 1. But that's an accident. This identification only happens when at 2. For all the larger dimensions we're interested in, we won't have this, and it really is SP2 that we're interested in. Okay, so now we have so this QL algebraic group was contained in GL2 with QL coefficients, and now we have a QL algebraic group that's sitting inside SP2 with QL coefficients. Okay. All right. We're making progress. The next step is we want to be working over the complex numbers. So let's pick an embedding. Call it iota of QL into C. Okay, and then we can, via this embedding, we can base change. So now let's let, say, G. The notation is getting ridiculous, but we'll be able to forget it all shortly. So let that be the base change of our GL1 to C. So now this is a C algebraic group. Okay. Okay. Now, if we look at the C points in our C algebraic group, okay, this is a Lie group sitting inside sp2c, okay, which is where we wanted to wind up. Okay, we're not quite there because it's not necessarily compact. Okay. So now we're going to define our Sato-Tate group, which I'll denote ST of E, as a maximal compact subgroup of this Lie group. All right, done here. Okay, and one of the nice properties of Lie groups is that, at least in this setting, that the maximal compact subgroup is unique up to conjugation. Okay, so one exists, and it's unique up to conjugation, meaning if I have any compact group, it's conjugate to a subgroup of this maximal compact group. Okay, but recall there were two pieces in our definition of the Sato-Tate group. I need to give you not just a group, I also need to give you a sequence of conjugacy classes indexed by good primes. Okay, so let's do that. So for good primes P, and I'm also going to assume that they don't divide L. That's okay, it's still a finite set of primes I'm ignoring. So let M sub P be the image of our absolute Frobenius element. Under this sequence of maps. So we first apply our Galois representation to get into GL. Then we took the Zariski closure to get into GL Zariski. And then we looked at the QL points on that. And then we used our embedding to get into this complex, the C points of this complex algebraic group. And now that we're over the complex numbers, we can normalize. We didn't want to normalize earlier because we want our square root to be unique. So now we're going to define our normalized Frobenius matrix. So we're going to take the norm of our prime to the 1/2, I guess minus 1/2, times our Frobenius matrix. And now we'll note that the characteristic polynomial of this normalized matrix is equal to the normalized L polynomial that appears in the numerator of the zeta function for the reduction of our elliptic curve at P. And the roots of that characteristic polynomial, they lie in the unit circle by the Riemann hypothesis. So they look like E and their conjugate, and they look, because it's the functional equation, it looks like E to the plus or minus I theta. And now we can let our conjugacy class, X sub P, okay, be the conjugacy class corresponding to theta. Okay. Yeah, sure.
So up above you have this intersection with SP2.
Yeah.
Down here below, when you summarize it,
That is an excellent question, and it's going to come up again when we talk about in abelian varieties. So in this case, it's trivial because when I normalize, I got determinant 1, and SP2 and SL2 are the same. Okay. But that's only true in dimension 1. As soon as we go past dimension 1, that's no longer a trivial constraint, and it's reasonable to ask, how do I know that this actually corresponds to a conjugacy class? Okay? And the answer is the Weil pairing. So in fact, I wrote the image Arial representation is landing in GL 2G, but we actually know that it's going to go into GSP 2G, which I'll define in a moment. Any other questions? Okay. Yeah. It is not clear at this point. We're going to prove that it is in a moment. The question was, is it clear that the group we're defining is independent of L? And the answer is no, it's not clear. It's also not clear that it's independent of the embedding of QL into C that we defined, which is one of the reasons why I wanted to carry around all this notation, keep track of all the choices we made along the way. The image of GL lies in GSP. Okay? It does not, I mean, the determinants are going to be given by the norm of our prime. They're not going to be necessarily congruent to 1. I certainly am, yeah. I'm going to go through this all again when we do the general case of abelian varieties, so why don't we postpone questions on the details? Okay, but these are good questions to have in mind. Okay. But let's convince ourselves that what we've done works for elliptic curves. Okay? That it has all the properties we would like it to have. Okay, so theorem. So E over K, an elliptic curve over a number field. Okay, then up to conjugacy. So the Sato-Tate group, because we defined it as a maximal compact subgroup, it's only defined up to conjugacy. Okay. Up to conjugacy in SU2, we can say exactly what the Sato-Tate group of an elliptic curve is. It is either U1. This happens when E has Cm over K. Normalizer of U1. This is when E has Cm but not over K. Or it's SU2, and this happens whenever E has no Cm. Okay, so let's prove this. Now, you might be asking, why am I proving this? I just wrote this down at the beginning of the talk, but that's a totally different statement. Here, I was talking about an equidistribution result. Here, I'm making a claim about the Sato-Tate group as we just defined it through this construction. Okay, well, the proof is pretty easy. So the first case is, let me label these. Case 1, case 2, case 3. Okay, in case 1, if we're in this situation, the image of the Galois representation is going to be an abelian group. This is a standard fact, which I provide references for in the notes. And this means that GL is going to be sitting inside some Cartan maximal abelian subgroup. And inside GL2 QL. And this Cartan subgroup is going to split when we base change to C, if it didn't split already. And this means that it's going to be conjugate to a diagonal group, or the diagonal group, or a subgroup of the diagonal group. And this is going to mean that we wind up with U1. Okay. In case 2, well, GL is not quite abelian, but it's going to be contained in the normalizer of a Cartan, but not in the Cartan itself. Okay, and this is going to imply that the Sato-Tate group is going to be equal to the normalizer of U1. I'll just recall that U1 has index 2 in its normalizer, so there's not a whole lot of room for anything to go wrong. And then the third case, well, we know from Serre's open image theorem that GL is going to have finite index, at least in GL2 with ZL coefficients. And this is going to imply that our algebraic group GL1s are, is going to be equal to SL2. And that's going to give us that the Sato-Tate group, when we take a maximal compact, is going to be equal to SU2. And of course, I could have written SP2 here. Okay. And then as a corollary to this theorem, well, it didn't depend on which L I used. The statement of the theorem didn't involve L. Okay. And it didn't involve any particular embedding. Okay. And at least in the case, except for the case of a non-CM curve over a number field that's not totally real, we've proved the Sato-Tate conjecture in exactly the way it was stated here, that the sequence of Frobenius elements that we have are equidistributed with respect to the push forward of the Haar measure on the Sato-Tate group, where the Sato-Tate group is now defined this way as opposed to just being cooked up as a group for which that's true. Okay. All right. So now that we've got dimension 1 under our belts, let's move on to the general case, or a more general case. One can define the Sato-Tate groups for a much more general class of motives than we're going to consider today. We're going to restrict ourselves to abelian varieties. The Sato-Tate group of an abelian variety, A over K, say of dimension G. Okay. And so just to recall that an abelian variety is a smooth projective variety that is also an algebraic group, and it turns out it has to be abelian. It has no choice. And if we have a nice curve C, so if C is a nice curve, well then there's a natural abelian variety associated to C called its Jacobian. It's an abelian variety, so they say this was a nice curve of genus G. We get an abelian variety of dimension G. And at least when C has a rational point, we can identify this with pick 0 of C. So this is the group of degree 0 divisors modulo principal divisors. And we can relate their zeta functions. So if we took reduction mod a good prime P, looked at the local zeta function there, it's going to look like LP of T over 1 minus T times 1 minus, well, I guess I should write QT where Q is the norm. And this L polynomial in the numerator is directly related to the characteristic polynomial of the Frobenius endomorphism, which acts on our abelian variety. It's just the reciprocal polynomial. So here, chi is the Kerr poly of Frobenius. Okay. And we can also relate it to the L function, associated to our abelian variety, which is just going to look like, take this L polynomial, plug in norm of R prime P to the minus S, all to the minus 1. Okay. So to study the Sato-Tate group of a curve is the same thing as studying the Sato-Tate group of an abelian variety. Of course, we could also study Sato-Tate groups of abelian varieties that are not necessarily Jacobians of curves. Things are slightly simpler in this scenario because we know that our abelian variety is also going to come equipped with a principal polarization, but in general, the Sato-Tate group doesn't care about that. Okay. All right. So let's run through a little more briefly this time, the same construction of the Sato-Tate group that we just did for an elliptic curve, and just note the things that are different. Pretty much everything is exactly the same. Okay, so Sato-Tate group of an abelian variety. Okay, well, we have a recipe to follow, so let's follow it. So step 1 is pick a prime L. And we now have an analytic Tate module, which is defined in exactly the same way. So we take the L to the n torsion of our abelian variety, and this is a free ZL module of rank 2G. And then we tensor with Q to get the rational Tate module. Step 2, we define our Galois representation, which is given by the action of the Galois group on the Tate module. We can think of this as automorphisms of this QL vector space if we like. And this is going to give us something that lands in GL2G QL a priori. So this is GL. It's going to be defined as the image rho L. Now, it doesn't actually make a difference for the definition, but we'll note, because this will be important when we get to the final state, the final step, this is actually a subgroup of GSP 2G. Okay. Then step 3, we're going to take the Zariski closure. And we're going to take it inside. So I could have written GSP, or I could write GL2. It's not going to make any difference. And then we define GL1 ZAR to be, we take as algebraic groups, we add this symplectic constraint. Okay, which, so thinking of this SP2G as an algebraic group over QL. So this is a new QL algebraic group. Then we pick an embedding. And base change. So we now have both, actually it'll be relevant for both. So we have both GL ZAR and GL1 ZAR. And they're now C algebraic groups. And then we define the Sato-Tate group as a maximal compact. And of GLI 1 ZAR, the C points. Okay, so that's a Lie group. This is going to, the fact that, so this is inside SP2G. So when we take a maximal compact, this is going to put us inside USP2G. So this is, so these are 2G by 2G matrices with complex entries that are both unitary and symplectic. Okay? So this is the compact form of the symplectic group, as some people like to call it. And then last step, for good primes P not dividing L. As before, we take our matrix, the image of Frobenius, absolute Frobenius element. So this is going to be, we're doing this in our base changed. Okay, and we take, I'm going to write it this way, just for simplicity. So we're going to take the conjugacy class in the Sato-Tate group. We'll take the conjugacy class of our normalized Frobenius matrix. Okay, and we now need to justify that last step, okay, with two remarks. First remark is that this matrix, this Frobenius matrix MP, is semi-simple. Since we're working over C, that means diagonalizable. And this is a non-trivial theorem of Tate. I mean, this is part of where this is contained in the paper where he proved the Tate conjecture for abelian varieties over finite fields. Okay? And then the second remark is that, as people have already pointed out, we were actually sitting inside GSP2G from the beginning, even though we didn't say that explicitly. Where, what is GSP2G? Let's define this. So here we're adding a sort of slightly weaker symplectic constraint. We want matrices that preserve a symplectic form up to a scalar. Okay? And where now we could take our symplectic form to be, so this would be take a 0, a minus G by G identity, and then a G by G identity down here, and then 0. Okay, so that's a 2G by 2G matrix. And our lambda is going to be forced to be in the multiplicative group, or I could write that as GL1, because the determinant of these guys are all non-zero. And then we notice that if we take 1 and 2 together, this implies that, in fact, our last step is justified. This normalized matrix is conjugate to some element of the Sato-Tate group. And the reason is it's semi-simple and has determinant 1. It's going to generate a compact group, and every compact group is conjugate to a subgroup of our maximal compact. Now, in the general definition of Sato-Tate groups for more general motives, this semi-simplicity is not known. So what we do instead is we take the semi-simple component of this matrix. So we use the multiplicative Jordan decomposition. We know we can write it as a product of a semi-simple matrix and a unipotent matrix, and we just take that semi-simple piece. We could do this, we could make this simpler by just working at the level of characteristic polynomials, but this is actually a slightly finer statement, even though in practice, all we really are studying is the distribution of characteristic polynomials. Okay, question?
Yeah, now that we don't have a preferred polarization, why are you intersecting if we don't have a particular parity?
Yeah, so I guess implicit in here is the fact that our abelian variety is polarizable, and so we can put a pairing on it. So we're just choosing one. It's not going to make a difference where we wind up with the Sato-Tate group. I think that'll become clearer as we move along, but if you prefer to work in the category of principally polarized abelian varieties, I'd be happy to do so. Okay. Any other questions? Okay. Sorry, can you ask the question again? That's probably... No, I think I had it right. So MP was the image in GLI Zariski, no 1 on it. Yeah, I can't put a 1 on it because the determinant is going to be equal to the norm of the prime. Okay. Any other questions? Okay. All right. So now that we have a Sato-Tate group, I've proved to you that at least when G is 1, it doesn't depend on L or the embedding that we chose. And we'll see in a little while that that's also true for G up to 3, and more generally it's true in any abelian variety for which the Mumford-Tate conjecture is known to hold, okay, which includes all abelian varieties of dimension up to 3, but also a lot of other cases as well. Okay, but now we'd like to study this Sato-Tate group a bit. We're going to start by studying the identity component. So we wound up with a compact Lie group, but that compact Lie group need not be connected. There was nothing we did along the way that guaranteed that that would happen. And a lot of the interesting cases come up when it's not connected, but let's focus on the identity component. Okay, so now we want to set things up, we're going to relate this to the Mumford-Tate group, and the Hodge group. So to set this up, we're going to first embed our number field into the complex numbers, and we're now going to work with the base change of our abelian variety to C. So this is a complex abelian variety. Then we know that our complex abelian variety, this is isomorphic to a torus. So CG mod some lattice lambda. We could even recover this lattice explicitly as the kernel of the exponential map from the tangent space at the identity mate. But it's not just any complex torus. It's a torus that is at least polarizable. Well, it doesn't come necessarily equipped with a polarization, but I could, if I put a polarization on my abelian variety, I can put a polarization on the torus. And just to remind or inform those who don't know what this means. So in the case of a complex torus, this means a polarization is a Riemann form. So going from I mean, I'm sort of fixing an isomorphism of our vector space with CG here just to make things a little more concrete. This is a positive definite Hermitian form. And it has the property that if I take the imaginary part of its image when I apply it to elements, pair up elements of the lattice, I wind up with an integer. Okay. So there's equivalence of categories between complex abelian varieties and polarizable complex tori. For those who are used to working in the world of elliptic curves, it turns out in genus 1, every complex torus, in dimension 1, every complex torus is polarizable, but once you go past that, that's not true. Okay. So you need to keep this in mind. Now we could identify, and we will, identify this lattice. We could think of this as the first homology group of our complex torus with z coefficients. Okay. And then we could even tensor our lattice with any ring we like, say. And we could, I'll define this first. So this is just tensoring over Z with our ring R, and then we could identify our lattice with homology with coefficients now in R. Okay. And so this, by the way, this for those who aren't familiar, the word polarization here might seem strange if you're used to polarizations of abelian varieties being defined as an isogeny between the variety and its dual, but it turns out you can take a polarization on the abelian variety and turn it into a Riemann form on the corresponding complex torus and vice versa. Okay. All right. So we can think of so we have this lattice, lambda, and we have this torus. So we can think of our abelian varieties, our abelian variety A, in two different ways. We could view it as a complex Lie group, but we could also view it as a real Lie group. And this implies that if we now tensor our torus with R, so we're going to get a real vector space of dimension 2G, this admits a complex structure. It's completely determined by this isomorphism over here. So by complex structure, I just mean homomorphism from C into the endomorphisms of our vector space. Okay. In other words, another way of saying this is that lambda H is an integral Hodge structure, pure of weight 1 or minus 1, depending on how you like to think of weights. Okay. Now we're heading towards the Mumford-Tate group, which is a Q algebraic group. So now our problem is we're coming in from the other direction. Before we were starting with something over a number field and QL, and we were trying to get into C, desperately trying to get into C. Now we want to go the other direction. We have something over C, and we desperately want to get back to the world of number theory. Okay. So we're going to view our complex structure. We're going to sort of forget about the additive part. We're going to view, or the fact that it's actually sitting inside a ring. We're going to just view it as a group homomorphism, continuous, from S, the Deligne torus, which I'll define in a moment, to GL of our real vector space, our 2G dimensional real vector space. And we're going to view this as a morphism of our algebraic groups. Okay, so what is S here? S can be defined as the restriction of scalars from C down to R of the multiplicative group. Okay, so this algebraic group, so this is a real algebraic group. It's called the Deligne torus. And the fact that that this is actually possible, that we can actually define H as a morphism over R as opposed to over C, is implied by the fact that our torus was polarizable. It wouldn't be true otherwise. Okay, and then the last thing we want to do, last piece of setup, is we're going to embed U1 into our Deligne torus. Okay, and I actually leave it as an exercise to spell out. There's a weight map and there's an embedding of U1. But leave that an exercise in the notes to spell out the details. It's a fun and not difficult exercise. And this gives us a map from U1 into GL lambda r, our 2GR dimensional R vector space. And the image of this map has eigenvalues, say U and U inverse, each with multiplicity G. And for those who know a little Hodge theory, this has to do with the Hodge number. We have two non-trivial Hodge numbers, and they're both equal to G. This image is called the Hodge circle, which will be important to us a little later. And in more general settings, this image, the eigenvalues we get and the multiplicity they have is going to depend on the Hodge numbers. But for our abelian variety case, life is very simple, so we don't need to think about that too hard. Okay. So now let's define the Mumford-Tate group and the Hodge group. So the Mumford-Tate group so here we're going to take the Q-Zariski closure of the image of our Deligne torus sitting inside GL lambda R. And what do I mean by this? So this image of this torus is sitting inside the real points of this, sitting inside this real Lie group. By the Q-Zariski closure, I mean take the smallest Q algebraic group that contains everything. Okay. And this is going to be a subgroup of SP2G as an algebraic group over Q. And then we define the Hodge group as analogously. So now this is going to be the Q-Zariski closure of, now we're going to restrict ourselves to the Hodge circle. So we're going to take H of U1. U1 we embedded inside our Deligne torus. And this is going to be, sorry, I made a mistake here. This is in GSP2G, and this guy is in SP2G. And in fact, we'll find that, so I give notations here. So MT of A for Mumford-Tate, HG of A for the Hodge group of our abelian variety A. So HG of A is equal to the Mumford-Tate group intersected with the symplectic group. One often sees this as an alternate definition. And one of the reasons, I won't use this in this lecture, but I'll just note one of the reasons people care about Hodge groups is that if we take the Q endomorphism algebra of our abelian variety, this is isomorphic to take our rational Hodge structure and look at the endomorphisms fixed by the Hodge group. This is an isomorphism as Q algebras. And just a word on these integral Hodge structures. You can relate these, there's an equivalence of categories with abelian varieties, complex abelian varieties, and the rational Hodge structures there's an equivalence categories to complex abelian varieties up to isogeny, because sometimes it's useful to work in both cases. Now, Deligne proved that the identity component of GL Zariski, oh, by the way, I didn't mention this, but this is often called the L-adic monodromy group. So the Zariski closure of the image of the L-adic representation. He proved that this lies inside the Mumford-Tate group once we tensor up to QL. And the Mumford-Tate conjecture is that inclusion is actually an equality. And I'll just, this is known, this Mumford-Tate conjecture is known in particular whenever the dimension G is less than or equal to 3. And I'll refer you to the paper of Banajak and Kadlaya, who basically are applying results of Moonen to get this explicitly. Banajak and Kadlaya also formulate So we should note that the Mumford-Tate group, this is telling us something about GL ZAR, but we define the Sato-Tate group in terms of GL1 ZAR, which is going to correspond to the Hodge group. So an equivalent statement of the Mumford-Tate conjecture is that the Hodge group, when we tensor up, is going to be equal to the GL1 ZAR when we intersected with the symplectic group. Okay. So the Mumford-Tate group is only going to tell us something about the identity component of the Sato-Tate group. It can't tell us anything about the component group. But there is a more general version, which I'm not going to say anything about, but I'll at least note its existence, called the algebraic Sato-Tate group, or algebraic Sato-Tate conjecture, is that there exists a Q-algebraic subgroup called ASTA, sitting inside SP2G, such that GL1 ZAR is equal to the algebraic Sato-Tate group A. Okay. All right. So I think, yeah, it looks like I am out of time. The next step we'll cover next, but maybe I'll just say a few words about it because it's relevant for the project team groups, is to analyze the component group of the Sato-Tate group. And I think what I'll do is just state the theorem so that you can be free to use the theorem, and then we'll give the proof maybe next time, or maybe I'll refer to the notes for the proof. Okay, so we have an abelian variety over a number field. There is a unique finite Galois extension unique up to fixing some algebraic closure in which everything is sitting in. This is unramified outside the bad primes of A. And has the property that for every subextension, including the trivial one, we have isomorphisms. The Galois group of L over F is isomorphic to the Sato-Tate, the component group of the Sato-Tate group. So STA. So in particular, if we want to know what the component group is, it can be realized as a Galois group. So if you can figure out this field L, you're good. And the nice thing about this theorem is this also there's no mention of L or an embedding here. So the component group is independent of our choice of L and the embedding that we use to define the Sato-Tate group. Okay, I think I better stop there.
Questions for Drew?
Yeah, so this last theorem reminds me of the main theorem of class field theory. Can you sort of put
well, so the proof is very simple, but it's sketched out by Serre in a section of his book on NX of P, and mind-bogglingly, I didn't notice it until I was preparing the lectures for this. And if I had known this theorem, if we had known this theorem when we were classifying the Sato-Tate groups in genus 2, it would have made our lives a whole lot simpler. Yeah, so maybe what I'll do is go through the proof at the beginning of the next lecture, because I do think it's remarkable, and it's a very simple thing to prove. Okay.
Hey, is there an abstract characterization of the Sato-Tate group similar to the abstract characterization of the Mumford-Tate group?
Yeah, so an alternative way to define the Sato-Tate group is takes a motivic approach. Sarah laid this out in his motivic Galois group paper, actually well before the construction that I'm using, which appears in lectures NX of P. But one needs to be very careful about what you mean by the word abstract, because as I've noticed, as I've noted, and I'll show some examples of this next time. With the definition that I've used, it's very important that we're seeing it as an explicit subgroup of, in the odd weight case, of USP2G.
Big question. So one very rough heuristic for BSD is supposed to be that if you have positive rank over Q, so you have infinitely many points, then you should get more points than expected when you reduce your elliptic curve mod primes, which would seem to run kind of counter to this equidistribution thing. If your abelian variety or elliptic curve has high rank, do you expect there to be some sort of slowness in the equidistribution?
Hold on, if I can get this. I think I can best answer your question with a demonstration. So this is a rank 28 elliptic curve, the highest rank elliptic curve that we know. And as you pointed out correctly, the distribution of Frobenius traces is very skewed. So surely, if any elliptic curve was going to violate the Sato-Tate conjecture, this would be a good candidate. Doesn't look like it. Hold on a second. Yeah, I didn't mean to be facetious. The point I'm trying to make is that the Sato-Tate group is really an asymptotic statement. It just doesn't see this. Rank 28 means nothing when you're taking primes out to infinity. An extra 28 points, who cares? Yeah.
Are you able to make quantitative statements about how fast it converges, the distribution converges to the Sato-Tate distribution, let's say in terms of the conductor of the curve?
Yeah, so I think I got this question in the first lecture as well. I'd refer you to the paper by Jesse Thorner, has an excellent paper in archive on this, and also the paper of Alina Bakur and Karen Kedlaila, who look at effective versions of the Sato-Tate for the elliptic curve case under GRH, you do need, and in some cases even more hypotheses. It's very hard to prove anything without some assumptions. Once you go past dimension 1, though, I'm not aware of any results in this direction. But Jesse would be a good person to ask.
All right, let's thank Drew again.